Uh, Welcome all of you, all the participants of ICSGRC. I'm from University Technology Mara, Malaysia, and it is my privilege here to share with you one of the papers entitled Implementation of Kinematics Bicycle Model for Vehicle Localization using Android Sensors. My name is Skokman Ng, and my co-authors are S.A.C. Abdullah, A. Ahmad, and J. Johari, and all of us are from the Faculty of Electrical Engineering, University Technology, Mara, Shah Alam, Malaysia. So today I will be the presenter in this ICSGRC 2020. And the content of my presentation will include the introduction, objectives, the methodology of the research, results and discussion, conclusion, and some recommendations for future works. So let's come to the introduction. As I will be talking about vehicle localization, here localization is actually a fundamental requirement for autonomous driving vehicles. Okay? Vehicle localization was developed in order to determine the vehicle position and location accurately on Earth's surface. Okay, when we have the actual location of the vehicle, it actually can assist other systems such as the vehicle navigation systems, as well as the vehicle path planning systems. Okay, some of the methods of localization include simultaneous localization and mapping, also known as SLAM, the global positioning systems, depth reckoning, as well as sensor fusion. Let me use a few graphics to illustrate some of these methods. Okay, the GPS uses GPS satellites to ascertain the location of the vehicle on Earth's surface. Okay, right. So now we also have real-time kinematics to have to achieve centimeter accuracy for the vehicle. Depth reckoning is a method whereby the vehicle's subsequent position on the Earth's surface is being determined with relative to its previous position. So we will use some of the sensors such as inertial measurement units, as well as also the positioning sensors and the odometry sensors, to aid that reckoning. Okay. SLAM is the simultaneous localization and mapping. Okay, it is using the LiDAR, the light detection and ranging sensor, to collect the data from the environment into a map, a 3D point cloud map dimensional as shown in this picture. So after that, we will use feature extraction methods to ascertain the vehicle location in the 3D map. So this is called SLAM. And finally, we have the sensor fusion, whereby the different sensors like LiDAR, cameras, radar, GPS, and IMU can actually be integrated and be fused for even better localization accuracy. So these are all the methods that have been established. So what is the research motivations here? Okay, in view of the higher cost in high-grade sensors, smartphones that contain position and initial sensors could possibly provide a low-cost solution for vehicle localization. And furthermore, platforms such as MATLAB Mobile provide functions to read these sensor measurements from the smartphone. So hence, we want to, the objectives of this work is that we want to develop a low-cost vehicle localization via implementation of Kinematics bicycle model by using MATLAB Mobile and Android phone sensors. So Kinematics bicycle model is actually a depth reckoning method. So we are actually implementing depth reckoning using the low-cost Android phone sensors. And subsequently, we want to evaluate the performance of this localization method, okay, using these sensors. Let's come to the methodology. Right, let me just explain a bit about the Kinematics bicycle model. The Kinematics bicycle model is a two-wheel model, which is similar to a bicycle, but actually it is applicable to a four-wheel vehicle, such a car. All right, but it is based on a two-wheel models. Okay, so it basically says the movement of the vehicles in the XY plane, whereby the velocity along the x-axis is given by the velocity of the vehicle multiplied with cos bracket psi plus beta. Psi is actually the heading of the vehicle with respect to the x-axis. That's psi. And beta is actually equals to arctangent of bracket LR over LR plus LF tangent of delta F. LR is actually the distance from the rear view to the center of the vehicle. And LF is the distance of the front view to the center of the vehicle. Delta F is the steering angle. So by having this information, we can actually calculate for beta. And hence, we can be able to calculate the velocity along the x-axis as well as the velocity along the y-axis. So by using equation 1, 2, and 5, we can actually calculate the displacement as well of the vehicle in the xy plane. And finally, we can map its path, okay, when we are able to calculate the displacement. So this, we come to the MATLAB mobile application now. This MATLAB mobile application is an app that can be installed in the smartphone. And when the app is being opened, it can actually show you all the sensor readings from the smartphone. Okay. One of it is the position sensors that can give you the latitude and longitude, all right, as well as the speed. Okay. And another one is the acceleration sensors, the orientation sensors, and also the angular velocity sensors. So all these sensor readings can be read by the MATLAB mobile, and it can be sent to a MATLAB session in the laptop. Okay. So for this work, we are using a Samsung Note FE smartphone and a Dell laptop Core i5 processor, 2.4 GHz, 64 bits OS to perform the KBM mapping. All right. So the smartphone is being interfaced to the laptop via a Wi-Fi communication. So all the readings in the sensor, all right, which is read by the MATLAB mobile, will be sent wirelessly to a MATLAB session within the laptop. And then the MATLAB session, the algorithm of the MATLAB is given as this. Okay, first, the most important thing is that because that reckoning is a relative positioning, the most important thing is that we need to ascertain the vehicle initial position x0 and y0 and store it as in the xy data structures. Okay, then we obtain the timestamp, and then the MATLAB session will also read the angular velocity from the MATLAB mobile, the angular velocity of the z-axis. It will also read the speed of the vehicle from the MATLAB mobile and read the azimuth, which is the heading, the vehicle heading from the MATLAB mobile. Okay, and then it will obtain timestamp T2. Okay, T2 and T1 simply give us the elapsed time within that particular iteration of the algorithm. All right, and then beta can be actually calculated by the angular velocity of the z-axis multiplied with the elapsed time T2 minus T1. So hence, we can get beta, the orientation angle. All right, and once we have beta and the azimuth, the velocity along the x-axis is given as v cos psi plus beta, and the velocity along the y-axis is given as v sine psi plus beta. Right. And subsequently, the displacement along the x-axis is given as x plus the velocity along the x-axis multiplied with the elapsed time. And the displacement along the y-axis is given by y plus the velocity on the y-axis multiplied with the elapsed time. And each displacement is being stored in the xy array. So hence, when we keep on looping, when we keep on, this loop will keep on being implemented, and there will be many xy points being stored in the xy array, okay, until we stop logging. Yeah? So in order to map the KBM path, we have chosen two locations. Location A is the road encircling the Faculty of Electrical Engineering, UiTM Shah Alam, which is the length is approximately about 700 meters. And location B is a road encircling a small residential area at Bukit Rimau Shah Alam, which is approximately 300 meters. Okay, right. So this is the results. We have developed actually a guided user interface to enable easier communication between the smartphone and also the laptop. Okay, so the connector on button in the GUI will enable the communication via Wi-Fi between the smartphone as well as the laptop. The start button is when we want to start implementing the logging. We press the start button. We press the stop button when we stop logging. And then you have a save data button to save all the log data into an Excel file. And finally, when we press the analyze data and selecting the Excel file, this analyze dialog will actually plot the whole path that has been traveled by the vehicle. All right. So this is the picture of the actual and KBM map path at location A plotted using Google Earth. Okay, the red lines is the actual path, whereas the dotted blue lines are the map path. Okay, you can see that there are certain parts like those that being labeled in the yellow circles. You can see those dotted lines actually deviated a lot from the actual path. Okay. And this is the Google Earth plot for the actual path and the map path at location B, which is the small, enclosed residential area at Bukit Rimau. So from the map path, we can actually calculate the mean absolute error, MAE, and the root mean square error. Okay. At location A, which is the Faculty of Electrical Engineering, we can see that it reveals a bigger difference between RMSE and MAE compared to location B. You can see that MAE and RMSE is not very close to each other. And this simply just signifies that there are variances in the data, in some individual data in location A, all right? Therefore, the RMSE and MAE are not closer in agreement. Okay, what is the reason? Okay, one of the reasons is that this may be attributed to GPS positions deviation as the vehicle path were mainly blocked by high-rise building in location A. Okay, so the MANLab Mobile is developed in such a way that it derives speed from GPS positions. So therefore, when the vehicle is moving in high-rise building and the GPS is being affected, so the speed may not be that accurate, and hence it will affect the localization accuracy. And in location B, it is much better. It reveals MAE and RMSE, which are in closer agreement. Okay. The lower MAE in location B may be attributed to more accurate GPS readings, as the GPS signals were not obstructed by any high-rise building, thus resulting in more accurate vehicle speed. Right. So the conclusion is, based on the experimental results, the actual path and the path traveled using Kinematics bicycle model are identical. Now, but however, with the mean absolute error, okay, ranging between 2 to 6 meters, the Android sensors are still far from being applicable for accurate vehicle localization. And we know that this is due to the inaccurate speed readings that rely on GPS, which can be affected by multipath effects. In addition, the initial sensors drifts may need to be addressed. So for future recommendations, for further works need to be done to improve the initial sensor drifts by using filtering and state estimation, such as Kalman filter. And on another note, okay, the accuracy of the map path may also depend on the quality of the sensors inside the smartphone. Okay, since we are using a Note FE, is considered a quite a good quality phone. But however, maybe in the future, we can further investigate by comparing the performance of low-end as well as high-end smartphone brands, right? To see whether the quality of the sensors will affect the localization accuracy. So with that, I hope that this work has shown us that Android sensors can actually be used for autonomous vehicle localization. Not only that, it can be used even for robotics application to localize the actual location of a robot. Yeah. So that's all from me, and thank you. I want to say thank you to all of you for listening to this presentation, and hope that all of us will have a good time in the conference. Thank you very much.